So throughout the course, we always talk about that the industry needed lightweight cryptography more than 20 years, but cryptographers start working on it for the last 10 years, let's say, maybe 15. But there was a time gap between the need and this caused a lot of disasters actually, because manufacturers tried to implement their own algorithms instead of asking cryptographers. They designed their own algorithms, and this caused some disasters actually. So one example is the Mifare classic cards, because these are a good example, because these smart cards, actually let me read from the slides. These were produced by NXP semiconductors, used in contactless smart cards and proximity cards. And NXP, as far as I know, is the world-leading company in this area. So these cards were produced more than produced more than 10 billion smart card chips and 150 million reader modules. So as far as I know, this was the most used smart card in the world, but maybe lately it changed, but they're still in use, by the way. So it uses a STIM cipher called Crypto1. So actually this is the problem, and this is what we are going to talk about. So after the AES competition, cryptographers thought that they had a perfectly good symmetric key algorithm, because AES was fast on software and hardware and it was secure. So people thought that AES can be used everywhere. But smart cards has a small area, and these Mifare classic cards don't run with battery. So they have to use very small amount of energy to run the encryption, and they need to use small amount of hardware area to implement the encryption algorithm. For this reason, instead of trying to fit AES inside the card, they designed their own algorithm, which is very simple, which I'm going to show it to you in the next slides. But the target applications were public transportation, and London's Oyster cards were Mifare Classic 1K cards, by the way, but they changed it after it was broken. But other target applications are electronic toll collection, loyalty cards, event ticketing, car parking, which I'm very familiar because in Turkey people use it for car parking. And some loyalty cards are still Mifare Classic 1K, but they are also used in many universities. So these Mifare Classic cards are still commonly used, and I will tell you if it is secure or not at the end. So what is the problem? So the following ISO standard actually provides some guidelines for contactless cards. So identification, contactless integrated circuit, and proximity cards. So this standard provides for these cards physical characteristics, radio frequency, power and signal interface, initialization and anti-collision, and transmission protocol. So from this document you can see what the standards are. But the problem is that Mifare Classic is not compatible with the fourth one, the transmission protocol. So this is why actually initial attacks were using this weakness, let's say. So how can you know what kind of smart card you have? So if you have an Android phone, you can install some apps, and NFC tools, one of the things I use. So if you have an NFC compatible Android mobile phone, with such an application, you can just bring your card next to the back of your mobile phone, and you can see the details like this. Here you see it says that this is Mifare Classic 1K. 1K actually means the amount of memory the card has. And as you can see, this ISO standard is not supported with this card. This serial number is kind of unique, but it is not a secret. And as you can see, we have 16 sectors of 4 blocks. And actually all of these sectors has 2 secret keys, and these secret keys are 48 bits, which is short, but the attack doesn't come from exhaustive search actually, which we will see. So Crypto One Steam Cipher is designed like this. So this picture actually kind of explains the whole algorithm. You have a state of 48 bits, which is the same with your key size. You also have an input because during the communication, a random nonce is produced, so it is fed from here, and the state is updated with this input. And the output is produced from here. As you can see, there are some functions, FA, FB, and FC, but these are very simple functions, and they only perform operations like AND, XOR, and NOT operations. Here, I will show you what they are. FA, as you can see, they take 4-bit input, and FC take 5-bit input, and the definitions are like this. But the important thing is that the manufacturer didn't actually publicly announce these details. Some academicians actually kind of reverse engineered it. They actually cut the card and looked at it with a microscope, and with following the circuit, they understood what the functions were. So it was a fantastic reverse engineering actually. And here are the functions and how it works. The L is actually these tap points. So how does it work? For instance, at the cafeteria, let's say that you are paying your meal by this card. So tag is your card, reader is the device that reads your card and takes money from your account. So when you get your tag to the reader, since the reader emits a magnetic field, the tag gets the energy from there and sends its unique ID serial number U, and randomly produces a nonce and sends it to the reader. So this is nonce of the tag. The reader receives this, and since the tag is produced by the people who also have the reader, from the database, the reader checks what are the secret keys of this card. And choosing one of them, most of the time, the first or the second sector's key is used. The reader answers to the tag, so performs some operations on this nonce and produces answer reader, and also randomly generates a nonce reader. But this set parentheses means that these are actually sent encrypted. Since reader knows the secret keys of the tag, reader encrypts its answer and sends it back. So this way, tag decrypts it and checks if the answer is correct. If it is correct, then tag now believes that reader is genuine reader. But if the answer is wrong, then actual tag produces an error. But if it believes that the reader is genuine, then tag produces an answer with respect to this nonce and sends it back to reader. Now reader decrypts it, and if the answer is correct, now reader also knows that the tag is a genuine tag. So this is the authentication process. After that, the reader subtracts the amount of money the tag has in the account from the database. So most of the time, the data is not stored on the card, but you can also store it since it has a 1K memory. But we don't suggest it because many attacks can come from there. So here is this explained here. Let me read it again. The tag sends its unique ID U to the reader. The reader then asks to authenticate for a specific sector. The tag sends a challenge NT. From this point on, communication is encrypted. The reader responds with its own challenge NR and the answer AR, which is the SARC function of this NT, which is actually written here. So the tag finishes with its answer 80, which also uses this function. So there were a lot of vulnerabilities, and the manufacturer improved these cards, hardened them, so latest versions don't have most of these weaknesses. So the main weakness was the weak pseudo-random number generator. So the problem is this: I told you that the tag produces a nonce here, but there are good publications about this in the literature. Academicians detected that the nonce produced by the tag is a kind of a time-varying answer. So if you wait a little bit, and this in milliseconds they know this number, the tag produces the same nonce. And producing the same nonce actually equal to using the same one-time pad key twice. So when you use the same nonce twice, the system is broken. This is why this weak pseudo-random number generator actually allowed the attackers to break the system, capture the secret keys of the card, but these were corrected in the hardened Mifare classic cards. Another weakness is the short key. So 48-bit key is really short. You can perform an exhaustive search attack on it. But the thing is that you have to perform the exhaustive search on the card, right? So you get the card to your reader and you try every key to check if this authentication is successful. So you have to try to authenticate yourself with the card 2 to the 48 times. The problem is that there is a delay introduced to the communication, and the authentication procedure prevents online brute force attacks. So this is why the short key is not the main problem here, but still it is short. There was a key stream leakage through error. It was 4-bit leak. So this was corrected in hardened Mifare classic card. So the idea was like this. So once you, as you, in the attack, you try to act like a genuine reader, but you are not. So tag sends you some nonce and its serial number. So you send some encrypted data, which is not important because since you don't know the key, you cannot answer correctly, but you try to answer anyway. So if your answer is incorrect, but the parity bits of your answer is correct, then the tag produces a 4-bit error. But this error is also encrypted. So since you know the 4-bit error, which is fixed, and it is XORed to the key stream, so from this you can capture the 4 bits of the key stream. So this is a huge weakness. So and this is important. This is also another case where we say that you shouldn't leak information about plain text, and this actually is the way it is done, because when this error is produced, you also learn the parity of a byte of the plain text. So this way you actually perform your attack, which we will see in a few minutes. Here I also explain it. Parity bits. Parity of plain text bytes are transmitted during communication. So this is actually a very bad idea. Actually, probably this is introduced to avoid errors through communication, but it also produces weakness, and many attacks come from here. Another weakness is the nested authentication. When authentication for a sector for which the key is known is completed, the reader can request for authentication of another sector. This time, tag sends an encrypted NT. So this operation is performed again, but this NT is sent encrypted. So this way, if you know the secret key of a sector, then you can perform an attack and capture the other secret keys of the other sectors due to this nested authentication. So let me summarize some of the attacks in the literature. These are card-only attacks, so these are online attacks. In order to perform them, you have to capture the card, and these are most of the time side channel attacks. So these are the number of traces you need to perform the attack. So initially there were weaknesses, as I told you. There were a weak pseudo-random number generator. So this way, Garcia et al. Produce an attack that can break the cipher in milliseconds. So you can capture the secret key if you get the card in microseconds. Then other attacks are also announced, but after the cards are hardened, when they remove this weak pseudo-random number generator, this is the best attack we have. as far as we know, which takes like around 10 minutes of data getting. So you have to capture the card. You have to perform the attack of major and verdult for 10 minutes, then give the card back to the owner, then perform some operations with your computer and obtain the secret key. So this is the attack that doesn't require a weak pseudo-random number generator, and it does not require the error code after a failed authentication, which is also, again, is not sent in the hardened Mifare classic cards. So there are also offline attacks, and which are also important. In this scenario, the attacker plays the role of a reader and tries to authenticate for a sector of her choice. She answers the challenge of the tag with 8 random bytes and 8 random parity bits for the reader's nonce and answer. With probability 1 over 256, since you are sending 8 random parity bits, the probability is 1 over 2 to the 8, which is this number. The parity bits are correct and the tag responds with the encrypted 4-bit error code. A success leaks, in this scenario, leaks 12 bits of entropy out of 48. So you don't know the key stream bits, but you get the parity of it. So this actually gives you some information, 4-bit from the error code, 8-bit from the parity bits. This is why you get 12 bits of information out of 48. So if you perform this attack like 5 times, it will be enough for you to get the whole 48 secret key. So we need to perform authentication since the probability is this, and you need 5 successful repetition of it. The expected value to perform this attack is to authentication of this many numbers, and this takes less than a second. So this means that if somebody has this card in their wallet, and if you stand next to them very closely, it depends on the antenna you are using. You can read the card from 5 centimeters to 40 centimeters if you have a good antenna. Then you perform these authentication attempts, get the data, and go home and perform an attack, which in GPU, they show that if you use GTX 280 GPU, it will take 9 days to capture the single key from this card. So a fantastic attack. So you can get this information while standing next to somebody, go home, use your GPUs and obtain the card. You can say that this number is kind of, 9 days is somewhat long. You can see that this is an old GPU, and the implementation was a naive implementation of the algorithm. So they say that if you have 16 GPUs like this, you can perform the attack in 14 hours. But we use the bit slice implementation technique and perform their attack, and observe that using a single GTX 970, you can get the key in 5 hours. So our newer GPUs can perform this attack in 1 hour, actually. So this offline attack is really successful, but these are not applicable to the latest hardened Mifare classic cards, because those cards don't send you the 4-bit error code. So this way you can break the older versions of the card. What can you do to hardened cards is as follows. You can perform the nested authentication attack. So given an encrypted nonce obtained through a nested authentication, the adversary can attempt to decrypt it using the candidate key. So here we have to warn you that since there are 16 sectors and there are 16 keys there, you have to know at least one of them to perform this attack. So this might sound unrealistic, but most of the time, people keep the default keys in the last sectors. So this way you can authenticate yourself by using the default keys, then try to obtain the other keys by performing this nested authentication attack. So if the candidate is the correct key, the parity bits will be correct. For a wrong key, a parity bit will be correct with probability 1 over 2. An encrypted nonce holds 4 bytes, thus 4 encrypted parity bits. Therefore, on average, 12 encrypted nonces are enough to get the key. Again, they show that it will take 1 month if you perform this attack with this GPU. And they say that 180 such GPUs can perform this attack in an hour, and the system should cost around $12,000, which is, at the time of writing, again, is not that bad, but now we have better GPUs, and as I told you before, we use the bit slice implementation technique. Since this is a very lightweight cipher, it performs really fast on GPU. So our implementation, bit slice implementation of this attack produced the result that we can perform this attack in 7 hours using a single GTX 970. Again, we have better GPUs now, so it takes like less than 2 hours. But if you have like more GPUs like we do, then you can perform this attack in minutes. So hardened Mifare classic cards secure only if all of the secret keys in the card are randomly generated. If one of them is kept like the default key, then we can break the other keys in this many hours. So this is why we always suggest to avoid these cards. But if you randomly generate your keys, then it is okay to use them. So there are many better versions of this card. They are also called Mifare, but not classic like DESFire or other versions. These cards use sometimes triple DES, sometimes AES. And I think triple DES also used in credit cards where you can pay in a contactless way. So you might think that since these cards are broken, they always produced better cards, but actually they produced Mifare Ultralight, which is much lightweight. As you can see, the name is Ultralight, and this can be broken too. But you might think that why they are doing this. This is actually depends on the cost analysis. If you need the card, you have to manufacture the card a lot of times, so you might choose something ultra light. And in this case, I know that these cards are used in public transportation, like in Portugal. So this is why they prefer to always produce something even more lightweight. So this is why we have this kind of smart cards, let's say.